All right. Well, so I'm here to tell you about CLAUDS, which is not a large project, not a large program, not an LP, but it has been referred to by some people on tax apparently as the missing LP because of it is quite a large program. And CLAUDS, of course, uses CFHT data. And where CLAUDS really shines is by combining CFHT data with data from Subaru, and I'll highlight some of that. So for background, very quickly, our interest is in how galaxies form and evolve, and to do that, we need to study galaxies over a large range of cosmic times and also over a large range of environments. And so cosmic time is illustrated here with the star formation rate density plot. As we all know now, the star formation rate density peaked at around redshift 2 and declined since then. So you want to probe all of that cosmic history and probe galaxies at these different epochs. You also want to look at different environments because galaxies are in voids, galaxies are in clusters and in other structures. And even very large surveys such as COSMOS, here's COSMOS overlaid over an embodied simulation, and you can see that it does capture some of the structures that exist in the universe, but even at 1 degree scales, 1.5 degree scales, it's still not really sampling things quite as well as you might want it to. So you want to do very large surveys, or at least bigger than COSMOS by a factor of several. And the state of the art today for that is the Hyper Supreme Cam, and we heard about that from Satoshi yesterday. So it's on Subaru. It's a 8-meter telescope, almost 2 square degrees field of view, and it just finished their 300-night HSC SSP Subaru Strategic Program project, and it's a fantastic survey. It images the universe in G band, R band, I band, Z band, and Y band, as well as some medium band filters. And that's awesome, but it doesn't have U band. And that is because you can see how the sensitivity drops down to short wavelengths. They chose to optimize for red sensitivity in their CCDs. And so they don't have U band. U band is very inefficient. So they just didn't do it. They didn't observe. Now, so why is U band important? There's many reasons, but I list 3 here. First of all, U-band is important to select galaxies at the cosmic noon, at this epoch, right? Through the U-band BXBM galaxy selection technique, the classic dropout techniques. So if you want to study this epoch, you really need U-band. You also need U-band to do good photometric redshifts. That I'll show you how U-band improves photometric redshifts, but at epochs L to redshift about 0.7, 0.8, you really need U-band to do, to help you with photoz's. And U-band is a good estimator of star formation rate, certainly if your galaxies are not very dusty, and most of the lower mass galaxies are not particularly dusty. So U-band is really helpful for star formation rates. So all right, so we need U-band, and so here's the plan. The plan is to do a survey called the CFHT Large Area U-band Deep Survey. And we do it on CFHT, or we did it on CFHT because the survey has been completed. We did it on CFHT because of CFHT's niche of U-band sensitivity and excellent seeing, right? We want seeing that matches HSC SSP, and we want depth that matches HSC SSP. So we want a reasonably large telescope. And the goal we set was to match the Subaru survey, certainly it's deep and ultra deep layers over 20 square degrees. And we did this with a program which lasted 5 semesters. We were allocated about 380 hours, which is 75 megacam nights. If you do the 5 hours per night conversion, that's recommended these days. And we did this as a PI type program. We didn't go for LP status because not only did we combine Canada and France time, but we also brought in China. At the time, there was no clear way to bring China into the LPs. So we decided to go with a PI type program. As I said, 5 semesters. And what we did is we added U-band imaging to the Hyper Supreme Cam survey imaging, which is GRIZY here, and we added U-band over here. This is the depth and the field layout for the clouds. You can the black circles are the HSC pointings, the Subaru pointings, and then the rainbow plots are the CLAUDS U-band data from CFHT. We have data in Cosmos, the extended Cosmos fields. The original Cosmos is the inner part of that, and then we have more data, about 4.5, 5 square degrees. We have data in Deep 2.3, we have data in LA's North 1, and we have data in the XMLSS field. And in Cosmos, we actually have 2 filters. That's why there are 2 panels. There's the U star filter, which was, we reprocessed the archive data for that. And then there's the new U filter, which is here. And you can see the depth and the area here. The black points are other existing or ongoing U-band surveys, and CLAUDS is here and here. We have 18.6 degrees down to 27.1 AB, and then we have a region of about 1.36 square degrees. That's about 0.8 magnitudes deeper than that. Right. So this is basically depths of CFHT-LS deep, but 5 times more area, or a bit smaller than CFHT-LS deep, but close to a magnitude deeper. Image quality, we wanted to have good CFHT image quality, and so here's a visual impression of that. And these here are the Subaru bands. So you can see we're going, we have comparable image quality to Subaru at longer wavelengths, and the depth also. You can see that all these fuzzy faint things appear in our images as they do in the Subaru images. I mentioned photo-Zs. U-band is important for photo-Z, so here's a comparison we did for that. And so on the left is just HSC, no U-band, and this is when you add U-band. And there are a couple of differences here. One set of differences is at lower redshifts over here, where you can see a big improvement. Without U-band, you get this aliasing here, this systematic effects here. U-band really helps there. U-band also improves high redshift interlopers. We actually do better than that now, but this is illustrative. And then at high redshift over here, you can see that you really do better if you have U-band. So hopefully I've convinced you that U-band is important. Now, the survey's been completed several years ago. We waited for HSC to catch up. But we've been doing science in the meantime, and so we have on order 20 papers published now, and more in preparation. So we have data papers, we have some luminosity function work, we have lots of stuff on galaxy evolution and more coming. AGNs, Lyman continuum escape, so ionizing photons escaping from galaxies. The U-band filter is very good for that. We have some other stuff coming. I don't have time to discuss any of this, except I'll highlight a few things which show you the quality of the data and just the power of the wide area and the depth. So one is UV luminosity functions. So this is, of course, combining U-band with the Subaru. Everything you'll see is combining U-band with the Subaru data. And so we have UV luminosity functions going from redshift 0.05, so essentially local, out to redshift 2. And you just look at the size of the error bars; they're tiny, and we're entirely dominated by systematics, not by shot noise in these measurements. We can integrate those and do the UV luminosity density of the universe. The stars are our measurements. You can see it going up nicely, especially in this redshift 0 to 1 region where measurements were scarce before. Even at cosmic noon, there's a lot of scatter in previous measurements, big error bars. We're cleaning that up. If you look at those UV luminosity functions in terms of Schecter parameters, here is alpha, here's phi star, here's m star. This is for the aficionados. You can see that all that increase back to redshift 2 is driven by the change in m star. Right, so galaxies were just brighter in the past than they are today. It's not a change in phi star. It's not a change in the faint and slope. But UV luminosity density is great, but star formation rate is even better. So here is a work that's about to be submitted on the star formation rate functions. So again, going from redshift 0.15 out to redshift 2, and then if you integrate these, you have the star formation rate density of the universe. We're doing a very good job measuring how it behaves, and also we can split it up by galaxy type here. Just want to show this because it's interesting. We can also do stellar mass measurements from the Uband through the optical, and we can do this out to about redshift 1 reliably. This is preliminary stuff that we really need to finish, but you can see that the red is quiescent, blue is star forming. You can see that we can do the points, I should say, with our bars are other surveys, right? Our measurements are these bands, so very, very small error bars, and you can see that we're going down to masses of 10 to the 9.5, even at redshift 1 in quiescent galaxies. We go deeper, of course, in star forming galaxies and at lower redshifts.
2 minutes.
We heard about, sorry, 2 minutes?
2 minutes.
Okay, perfect. So we heard about low surface brightness stuff. CFHT is good for that, and so it is also in our data. Here's some montage of interacting galaxies. You can see various tidal features, and that's actually a good way to find merging galaxies and interacting galaxies. So we looked at that we had a machine learning technique developed for that, and so here's the merger rate evolution out to redshift 1, and it scales as not unexpected. It's we're getting the right slope. So this is a promising approach. And of course, there's all this other stuff. So you can go to these papers online or ask if you're interested. I just want to mention what's next. So what's next is that we're going to make the catalogs and the images public, because the HSC images are now public already, but the Uband are coming from us. We're essentially waiting for this paper, the catalog paper, to be accepted, and that's already been submitted, so it should come out soon. We have the catalogs include not just CLAUDS and HSC, but also near-infrared data from BIRCam. So that's shown here in the red, so that's over 5.5 square degrees. And then, of course, the CLAUDS and HSC is over 18.6 square degrees, 18 million galaxies. I'll just show one thing from that work. This is photometric redshift quality assessment. We actually did things using 2 separate pipelines just to see, just to have confidence. One is using the classic schecter LFR. The other one is using the HSC pipeline, which we modified to work on non-HSC data, and the phosphorus code, which is a new code for photometric redshift. So these are the two sets. This is going to deeper magnitudes, and we're comparing against Cosmos 2020 redshifts, right? So we're comparing the Cosmos field, and you can see how well it's working. It's working pretty well. Right, of course, we have more area than Cosmos. So I'll wrap up with that. I'll just say that the catalogs are going to be public, conservatively by the end of this summer, but really it should be sooner than that, because the paper's already gone through one round of refereeing, and we plan to make these available as soon as we put the paper on archive. So with that, I will stop and go to questions.
Thank you, Marcin. Any questions? Okay, so.
From Laura Parker, will the Photo Z catalogs be public too?
Sorry, are you asking whether they will be public? The answer is yes.
I'm Marcin, Jean-Charles here. Just a question on the difference between it was LFR versus phosphorus.
Yes.
Where is the difference coming from?
Where's the difference coming from? They're using, they're slightly different codes. They use similar approaches, but they are different, and they use different template sets and so forth. A big difference, of course, is also between the schecter and HSC pipe, which are very different photometric codes. Does that answer your question?
Okay.
Hi, Marcin. This is Tracy Webb. I'm, as it may not surprise you, interested to know about the dusts. How well are you measuring the dust extinction, and can you place any constraints on what you might be missing dust of galaxies?
Well, dust is always tricky, and I think we're doing a pretty good job in the areas where we have infrared data, where we can have really the large wavelength coverage to be really confident that we're getting the right templates. The study with the star formation rate functions and star formation rate density that I showed, that's led by this student. Vincent Piquet, this fellow. So he has looked at infrared data, so beyond near infrared, to calibrate things. I am not sure that this survey, in general, though, is probably what you would want to use. The optical through the Uband through optical data is what you would necessarily want to use. Exclusively, they're really super focused on dust, right? You would like to have longer wavelengths to do a really comprehensive dust study, which as I said, Vincent has done, but bringing in additional data.